Now let's characterize what the solution to the cost minimization problem looks like. And I'm going to do it both graphically and mathematically for you. So to do it graphically first, look at the domain of the problem, of the cost minimization problem. We have K and L. We have an isoquant that we want to reach. This is the target level of production Q. And remember, these are the combinations of inputs K and L that yield that level of production. And what we want to find is what is the minimum cost combination of inputs at which that can be reached. And what you can think of is a series of lines that look like this, are linear lines, and each one of them is called an isocost line. And these are the combinations of points K and L that have the same cost. So these are points K and L for which RK plus WL equal a constant. Now, think about what are the properties that the solution needs to have. So lines out here are lines with higher costs. Lines out here, like this point is zero cost, are lines with very little cost. So it should be easy to you that to find a solution, you can think of sliding a ruler inwards until you find an isocost line that just touches like this the isoquant that you want to reach, and that point that just touches is feasible and it has the lowest production costs. So this will be the solution, K min and L min, to the cost minimization problem. Okay? And it's just given by the tangent of the isocost line and the isoquant line. Now let's characterize the properties of the solution mathematically. So first, to do that, we need to look at the slope of an isoquant. And we can obtain the slope of an isoquant at any point by noticing the following. If I take the production function and I take the partial derivative with respect to K for a marginal change on dk, and then I do the same thing with respect to L for a little change of dl, this basically tells me what is the change in production produced by a marginal change of dk and dl. And I'm interested in a change, let's say if I'm in this point, in a change in dl and dk, like this one, that leaves total production unchanged. So total change in production is 0. That equation tells me for any level of decay, what is the level marginal change in dl that will leave things unchanged. But from this, what I get is that dl over dk, which if you want is the slope of the isoquant at any point, is just equal to minus the partial of f with respect to k divided by the partial of f with respect to L. That is the slope of the isoquant when this is evaluated at any point. Now let's ask, what's the slope of the isocost line? Well, we know the equation here. We can solve for L in terms of K, and what we get is L is equal to the constant, let's say C bar, divided by W minus R divided by W, WK. But that implies that the slope of the isocost is this. So slope is minus R divided by W. Now, given that, what is the solution to the problem I'm going to give? It's going to be given by, I'm going to write it here in a square. So L min and K min satisfy two equations. First, it has to be a feasible level of production, so Q has to be equal to F of L min K min. And second, and also very important, the two curves, are tangent. In other words, the isocost line and the isoquant have to be tangent, so these two slopes have to be the same. So we have to have that the partial of f with respect to k divided with the partial of f with respect to L, that's the slope of the isoquant, has to be equal to R divided by W, which is the slope of the isocost line. Okay? There is a lot of economics in this optimality condition that we just derived, and I want to explore it with you in more detail. So let's look at each one of these terms. This term is called the MRTS, or marginal rate of technological substitution. And I want you to see through a little bit of a graphical argument what this means economically. So we have K, we have L, we have the isoquant, and the MRTS gives us the slope at any particular point. Let's say this. So the slope is minus the MRTS. Now, think about what this means economically. What this means is that suppose that we are at this point K, and we increase the amount of capital by a marginal amount, dk, so to K plus dk. What the marginal rate of technological substitution is telling you is by how much can we decrease labor without changing the amount of production. And what you can see is that it changes, the marginal rate of technological substitution changes across the isoquant. So for example, in the case depicted in the figure, the marginal rate of technological substitution is very high when capital is very low. In that case, increasing capital by a little bit allows you to decrease labor by a lot without changing the amount produced. You can think of it as kind of, this is always decay and this is the high of the change. Whereas here, when you have a lot of capital already, you may need to increase decay a lot just by if you decrease labor by a little bit, you will have to increase capital a lot to be able to keep production unchanged. Now let's think about what the right-hand side of the equation is. These are basically the relative prices of capital and labor, with capital on top and labor in the bottom. And let's think graphically also about the economic intuition of what this term means. We have these isocost lines that we saw before. These are the combination of prices of capital and labor that have a total equal cost, and we know that the slope was minus RW. What that means is the following. The relative price is telling you if you were to increase capital by 1 unit, how many units of labor will you have to reduce, let's call it minus delta L, to be able to keep the cost the same. Okay? When this relative price is very high, this is very steep, and it will mean that you will have to cut a lot of labor for every additional unit of capital that you want to do. And that's very intuitive, because when this is very steep, R is very high, and vice versa. So that's the economic intuition of what the relative prices mean. Now, given the intuition that we have developed, let's put it together to see why that relationship needs to hold at the cost minimizing combination of inputs. So suppose that it doesn't hold. And for example, say that we have that the marginal rate of technological substitution is greater than the relative prices. That's a case that looks like this. So if you draw K and you draw L and you draw the isocost line, and you also draw, sorry, that was the isoquant, you also draw the isocost line, let's say this one, and when you look at a point like this one, okay, what we have is that the marginal rate of technological substitution, which is here, is steeper than the relative prices of the isocost line. Now, it should be obvious to you that this point cannot possibly minimize costs, because any point in here, any point like that, has lower costs and same production. So basically, you could decrease costs by increasing capital by some amount and decreasing labor so that you stay in the same isocost line. So it cannot be the case that you are maximizing profits where this is greater than this. And you can move towards the right. You can increase capital. Now, what about the other case? So what if marginal rate of technological substitution is less than the relative prices? What if that is the case? Well, that's a case that looks like this. You have the isoquant, and you have the isocost line being flatter to the point of interest. So this will cut like this, say. And again, if you were looking at this point, that point cannot possibly be cost minimizing, because any movement to the right, to the left by decreasing capital that increases labor just to stay in the isoquant will keep production of change while reducing costs. So if you move to the left in particular, you again has lower costs and same output. So in both cases, when you're in an interior solution, you cannot have a violation of this condition. In other words, this must hold at an interior solution. Let me emphasize that I'm qualifying by an interior solution because in both cases, to construct the combination of inputs that had lower costs, we either had to increase capital here or decrease it here, and either decrease labor here or increase it there. So that can always be done on an interior solution, but as we will see in the next slide, may not be possible at a corner solution. Now, in most of the production functions that we will be using that are using economic modeling, corner solutions do not arise. But they cannot be ruled out in general theoretically, so you just want to make a couple of quick remarks about them, just in case you're asking yourself that. So consider two cases in which corner solutions can arise. Suppose that you're in a situation like this. This is capital, this is labor, this is the isocost line, and you have that the isoquant is like this. So at this point, basically, this marginal rate of technological substitution is steeper than the isocost line. Another way of seeing this is that if you were to continue the lines outside the feasible space, they will basically cross like that. Now that's a situation in which you were not constrained by labor, you would like to move in this direction, towards this. But that is not feasible because labor has to be greater or equal than 0. So in this particular case, you could imagine having a point like this that has L mean equal to 0, K mean greater than 0, that is optimum and satisfies that the marginal rate of technological substitution is greater than the relative prices. Now, you could similarly imagine a situation like this. It's basically the analogous situation, the opposite case. You have the isocost line like this again, and you have that the isoquant, again, is coming steeper here than the isocost line. So again, if you were to extend this beyond the range of feasible inputs, you will get that the isocost line was like this, and the isoquant was like this. So if you could, you would like to move in this direction, but it's not possible because capital has to be non-negative. So in this case, you could have a solution that has K mean equal to 0, L mean greater than 0, an optimum in the sense of being cost minimizing, and the marginal rate of technological substitution being less than the relative prices. Again, this is a theoretical possibility. I'm going to show you in example an optional problem that has this feature, just so you get familiar with that. But in general, don't worry too much about memorizing or dissecting this case, because we're not going to see it a lot.